Hello everyone, this is Dr. Syed Kazmi once again. Welcome to my YouTube channel, and today I'm going to talk about some of the advanced concepts in mechanical ventilation. I have already done two videos on mechanical ventilation. My first video on mechanical ventilation was to explain some of the basic terms which we use in pediatric mechanical ventilation. And my second lecture was a very brief topic giving you some tips on how to adjust different ventilator settings in different scenarios. So if you haven't watched out those videos, I'm giving the link right up here. So do click on the links and go and watch those videos and then come back and see this video. So again, I will start with again explaining these basic terms, and then I will move on to the mode. So you need to understand some of the basic terms. So the first important term is the IE ratio. So the IE ratio simply means inspiratory to expiratory ratio. Now this we have to set on the mechanical ventilator, because in most of the lung problem, it's usually the problem in the expiratory phase. So the problem is that somehow the child is not able to properly exhale the air because of some obstructions, in smaller airways or maybe even the larger airways. So we set the IE ratio. Normally we set it around 1 to 2 or 1 to 3. So simply mean, let's say if the total breath cycle is for 3 seconds, so 1 second would be for inspiration and 2 seconds for expiration, or it can be even 1-3 depending on whatever is the underlying pathology. So IE ratio simply stands for inspiratory to expiratory ratio, and for practical reason we usually set it 1 to 2 or 1 to 3. The other is a breath cycle. So breath cycle is the total amount of time taken for the complete breath. So inspiration plus expiration. So it could be anywhere. It could be 1 second, it could be 2 seconds, it could be even 3 seconds. Rate simply means the amount of breaths which is set on the ventilator that the machine has to give per minute. So it could be like 12, 14, 20, depending on the age and depending on the underlying pathophysiology, you can set the rate. FiO2 stands for the fraction of the inspired, the fraction of oxygen in inspired air, and normal FiO2 at the room air that we inspire all the time, that is 21%. So we set the FiO2 anywhere between 21% to 100%, but please keep it in mind that keeping FiO2 at 100% is quite toxic for the tissue. So usually if we have to keep it, we keep it for a small period of time, and then we have to titrate it down to some acceptable levels. Most of the time it should be less than 50% FiO2. So FiO2 can be set at the increments of 5. So you can go like, let's say 25% in FiO2, you can have 30%, 35, 40, so on and so forth. PEEP stands for peak expiratory and expiratory pressures, and this is the pressure at the end of the expiration, that is the end of the breath, which the mechanical ventilator keeps. So there is a pressure, still a positive pressure, kept inside the alveoli to keep them open. In other words, we want to recruit the alveoli. So if the alveoli are collapsed and not taking part in gaseous exchange, we have to push air to keep them open. So if they are open, there will be more gaseous exchange, and that would help in oxygenation. So for that, positive and expiratory pressure is usually maintained by the mechanical ventilator, and we usually set it around 5 centimeters of water, though it can vary in different conditions. And then last but not the least is the tidal volume. So tidal volume is the amount of air which would be pushed during every breath by the mechanical ventilator. So in pediatrics, we usually use around 4 to 6 mils of per kilogram of the ideal body weight. We can go up to 8 mils per kg of the ideal body weight, but usually high pressures in tidal volumes, like it can cause barotrauma. So that's why we usually go with low volume, so 4 to 6 mils per kilogram of ideal body weight. So that is the tidal volume, and it simply means the amount of air that would be pushed through every breath. Excuse me. Now coming down to the modes. So the modes depend on who does who takes over the job of respiration. So if the job is being done by the ventilator alone and the patient is not allowed to take spontaneous breaths, or the patient cannot initiate breath, we call it as continuous mandatory ventilation. So CMV simply means that the the ventilator is doing the job, the patient cannot initiate any breath, so it doesn't allow for spontaneous breathing. The other type of mode is the intermittent ventilation. So in intermittent ventilation, though mechanical ventilator is giving the breaths to the patient, but in meantime, if the patient wants to initiate spontaneous breaths, so the machine allows the patient to take spontaneous breaths in between in order to maintain some minimum respiratory rate. So that we call as intermittent ventilation. So these are the two broader groups of ventilation: a continuous mandatory ventilation where ventilator is doing the job, or it could be intermittent where it allows for spontaneous breathing as well. So you can set, like, IE ratio, you can set the rate, FiO2, PEEP, tidal, and then depending on who takes over the breathing, whether it's a ventilator that's doing the job or whether it's the patient that can also initiate, but you can have different modes of ventilation. And some of the common ones are, number one is assist control or continuous mandatory ventilation. So as I told you earlier, usually in this mode, the ventilator is doing the job. So patient is deeply sedated or he's comatose, he cannot make spontaneous breaths. So in other words, ventilator has taken the job of the respiratory centers and it's doing everything. So what you do is you set a fixed volume and you set all these parameters that I explained earlier, and the machine is then starts giving those breaths to the patient with a fixed volume. Now the pressure can vary, so the pressure can go up and down in order to maintain that volume that you have, you're fixed on the ventilator and the ventilator is giving that. So that is assist control or continuous mandatory ventilation. You can have the pressure control. In pressure control, what happens, you are controlling the pressure. So you set pressure, so you set a peak inspiratory pressure and then the machine maintains that pressure, but the volume varies. So the volume can be anywhere, it can go up, it can go down, but the pressure is maintained throughout the breath cycle. Then the third one is the pressure support. So the pressure support is different from pressure control because in pressure support, the machine is giving support during the inhalation part of the breath, while in pressure control, the machine is giving, is supporting both the inhalation and exhalation, while in pressure support it's just giving support, it's giving a sort of a push during the inspiratory force. And then we have got the SIMV, which stands for synchronized intermittent mandatory ventilation. So it's a combination where a minimum rate is ensured by the ventilator, and in between, if the patient is taking spontaneous breaths, so the machine allows for those spontaneous breaths and even supports it. So it can be pressure regulated or it could be volume regulated, and the machine simply helps the patient to generate his own breaths as well. So these are a few common modes that we use it. There are some other modes as well. I'm not going to go in the details of like CPAP and some other modes. These are the common ones that you need to understand. Now, it's also important to understand the waveforms that are displayed on the screen of the mechanical ventilator. So these are known as the ventilator scalars, and it's very important because you have to interpret these scalars. If anything is going wrong with the patient in terms of his respiratory physiology, it would be displayed on these scalars and you can pick them up and you can take some remedial actions. So for example, in assist control method, if we go through in assist control method, the volume is fixed. So you have fixed a tidal volume that is being delivered by the mechanical ventilator during every breath. The pressure varies. So if you look at this graph on the left side of the screen, just let me highlight this one. So if you see, the volume is fixed, so there's a fixed volume here which is going in during every breath, while the pressure varies. So the pressure can be one value, it can be another value, and then it can be a bit, it varies from breath to breath. While the flow, if you see, flow is positive, so the air is going inside, so you will have a positive flow during the inspiratory phase, and then you have got the negative flow because the air is going out. And then before the start of the next breath, what happened? It has come down to 0, and then a new breath is initiated. So this is the flow scalar. So in assist control, how would you know it's assist control? The volume loop would always be fixed, while the pressure would vary. So if you see, on this line, if the volume is fixed during every breath, you are looking at assist control mode. Also keep it in mind that if you recall your high school physics, pressure is inversely related to volume. So let's say if the volume is fixed, and on the scalar, if you waveform, if you see the pressure starts rising, like let's say on the green scale, you can see the pressure starts rising. So what would happen? Usually the machine has got control. So if the pressure goes very high, you start giving beep, 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 beep. So like, so if you are busy on your Instagram account or looking at your Facebook page, so you will be, you will be signaled by these beeps, and you have to run and see what's wrong with the patient. So if the higher pressures are generated, it simply means that the lung compliance has decreased because the volume is fixed. So if the volume is fixed and you need more pressure, it simply means the lungs are quite stiff. So that's why the machine has to push harder. It has to generate more pressures to push the same amount of air inside. And what can cause that decreased compliance? You can have fluid in the lung, like in ARDS. It can happen in pneumothorax. It can happen in pulmonary edema, so on and so forth. So that can give you an idea what's happening. In the pressure control mode, you will see graph like this. So what you will see is that the pressure is fixed. So in every breath, you'll see that the pressure is fixed, while the volume varies. The volume is varying with every breath. The flow, as I told you, it's the same thing, positive during inspiration and negative during expiration. Positive during inspiration and negative during expiration. So if you see where the pressure is the same during every breath, but the volume is changing, you are looking at pressure support mode. Now again, the same thing. So if the pressure is constant, like in pressure control, but if you see the volume is decreasing, like it's the same pressure, but the volume of air, it can't go inside. What does it mean? It means again the same thing, the compliance has decreased. The compliance has decreased. And again, like for the same reason, ARDS, pulmonary edema, pneumothorax, and a few other pathologies. So again, if the volume goes very low, the ventilator would start beeping again, and you have to rush to the patient and see what's going on, and you have to then take remedial action by tuning the parameters to bring it back to normal. So this was assist control, continuous mandatory ventilation. This is the pressure support, pressure control one, where you would see the same pressures and volume would change. And then let's talk about the pressure support. So the pressure support, I told you that the ventilator only supports the inhalation phase. So when patient himself triggers the breath, the ventilator will go to push because the patient is sedated. So the ventilator doesn't want that the patient has to work very hard to breathe in. Just give a push so that the air goes inside, and that pressure can vary from breath to breath. So that is what we call as pressure support. Now in pressure support and in pressure control, or even in volume control, the thing is that if you have to look at the pressures, looking at and diagnosing pressure problems is very important. The pressure phase itself, normally you would see if you are looking at the ventilator, it just shows you the peak inspiratory pressure. But the pressure wave itself is composed of two parts. There is a peak pressure and there is a plateau pressure. So what happens is, basically, let's say the machine is pushing the air inside. So the pressure would increase, like it goes up, it reaches a maximum, because the larger airways have got resistance. So that has to be overcome. So machine gives a hard push to start with. So the pressure would rise, let's say, up to 20 centimeter of water or 23 centimeter of water. That is the peak pressure. So once that pressure is reached, the air has come down to the lower levels of alveoli. So just keep in mind. So you are, pushing the air from here. The tube is here. So the pump, the ventilator is pushing it down with a force. So it has to go all through the larger airways down to the smaller airways to the end of the alveoli. So this pressure would increase. It would reach a peak that is known as the peak inspiratory pressure. So when the peak inspiratory pressure, it simply means that the air has passed through all the larger airways down to and it's reached the lower. Now what you need to do is that the pressure needs to be maintained at the alveoli. So alveoli are open, you need to keep this pressure so that the air remains inside the alveoli so that the gaseous exchange can happen. Now that is the plateau pressure. So the plateau pressure is the pressure which is exerted by the ventilator to keep the alveoli open. So there is difference between the peak pressure and the plateau pressure. The plateau pressure is slightly lower than the peak pressure, and normally if you look at the pressure waveforms, you can't see the difference between the peak pressure and the plateau pressure because there will be one wave. But there is a button on the ventilator which we call as inspiratory hold. So if you press that button, inspiratory hold, for 0.5 to 1 seconds, so what would happen? It would cut off the circuit. So if the patient has taken a breath, as soon as that breath is taken, inhalation, the ventilator cuts off. So the ventilator stops, like the valve stops. The air can't come out. So now the pressure is, which the ventilator is measuring, is equal to the plateau pressure. So you can see a graph like this. So if you press the inspiratory hold button, you would see that the graph suddenly changes from that waveform to like this. So there is a peak pressure. This peak is the peak pressure, and then you have got a plateau. This is the plateau pressure before the pressure starts dropping and it comes down to 0, or it comes down to PEEP, whatever PEEP you have set. So remember that the peak pressure is determined by the airway resistance. So if you have got a high wave, like a tall wave on the pressure one, so if the peak inspiratory pressure is going very high, it simply means the lung compliance is decreased. But why the lung compliance is decreased? There's some problem in the airway resistance. So either the tube is blocked or the larger airways have got some issue. But if you got a high plateau pressure, so a high plateau pressure simply means that there is problem in keeping the alveoli open. In other words, that is determined by the compliance. So if there is fluid in the alveoli, definitely you would need more plateau pressure to keep them open. Similarly, if there is pneumothorax or there is pulmonary edema, you would need more pressures, plateau pressures, to keep the alveoli open. So if the plateau pressure is increasing, it simply means that there is decrease in lung compliance, and you have to see some of the common causes which causes decrease in lung compliance. And if there is increase in peak pressure, then you know it's not issue with the compliance, it's issue with the airway resistance. You have to see what's going wrong. Is the patient biting the tube? Has the tube kinked? Has it blocked secretions in the larger airways? So you have to look into that, and you have to take remedial actions. Similarly, if you look at the flow, so the flow curve, remember because in inspiration the air is going inside, so you will get a positive, then in the expiration the air comes out. So if the air is not like reaching the zero, it simply means air is getting stacked inside. So it means over distension. We call it auto PEEP. So auto PEEP simply means that more and more pressure is being generated. So in that case, you have to give more time for the expiration. You need that air to come out. So simply what you can do is you would change the IE ratio. So you have to increase the expiratory ratio. So if you see a line like this where you get this thing and it comes down, and before it reaches it, there is another. So let me draw like this. So the wave is initiated here rather than reaching here. So it starts, the inspiration starts here. So you've got stacked air. This is the stacked air over here. So you need to take that air out, because otherwise this would lead to auto PEEP. And auto PEEP is not good because it will lead to barotrauma. So you need to give more time for exhalation. And the best way to do that, if you see over here, you have to increase the expiratory phase of the breath cycle. Okay, now moving on, as I told you earlier that in order to determine the plateau pressure, you have to press the inspiratory hold button for 0.5 to 1 second, and that would determine the plateau pressure. So keep that in mind, but otherwise it will not show you on the ventilator scalers. So you have to press that button, and also keep it in mind what's the difference between minute ventilation and alveolar. Your minute ventilation is actually the product of your respiratory rate multiplied by the tidal volume, and that determines your carbon dioxide clearance. So let's say if your respiratory rate is 20 and tidal volume is 50, you can determine your minute ventilation by multiplying the two. But alveolar ventilation is different. Alveolar ventilation means how much air is being accommodated at the, which is taking part in the gaseous exchange, and that is your respiratory rate, but you multiply it by the tidal volume minus the dead space, because your alveoli is where the oxygenation is happening, where the exchange of the oxygen and carbon dioxide is happening. Your larger areas, they do not take part in the gaseous exchange. So the air is still there, but it doesn't take part in the gaseous exchange. So that's why there is difference between minute ventilation and alveolar ventilation. So alveolar ventilation is more important. That's why, let's say if a patient is taking shallow breaths, so they are not helping their alveolar ventilation, because actually they are shallow breaths. So it's just like, going through the dead space. So you still have got a high minute ventilation, but the alveolar ventilation is slow. But if you take deep, slow breath, and then you slowly exhale, so that would actually mean more alveolar ventilation. That's why even in some of the traditional medicine methods like biofeedback and yoga and other things, they talk about breathing exercises, slow deep exercises. They say it purges your body of different toxins. I think probably they're talking about carbon dioxide clearance and other things. So what happens is basically when you take deep slow breaths, you are actually increasing your alveolar ventilation. But if you do panting sort of thing, where you have got shallow rapid breaths, well, it will just lead to more of air going in and out, but there is no much alveolar ventilation going on, so it's not helping your breathing. So keep that thing in mind. I hope that I have explained it in simple language. Okay, fine. Now, how to determine problems with the with these waveforms? I told you earlier, if the pressures are rising when the volumes are fixed, simply means low compliance. Similarly, if the pressures are fixed, volumes are dropping, simply means low compliance. Similarly, I told you increase in peak inspiratory pressure simply means increase airway resistance. That means more problem with the larger airways, either the tube is blocked or there are large secretions or the patient is biting the tube. If there is increased platelet pressure, simply means decreased lung compliance, could be because of pulmonary edema, ARDS, so on and so forth. Similarly, if you see a dip in the pressure waveform, it simply means flow hunger. Flow hunger means that whatever rate you have set, the patient needs more than that. So probably you have to increase the tidal volume, may have to increase the respiratory rate as well. Also, I told you earlier that the flow has to come back to zero before a new breath is taken. And if you see that the breath is initiated on this form, if the flow form is, the next breath is starting below this baseline, it simply means that there is auto PEEP and there is air trapping, and you need to change the inspiratory to expiratory ratio. Similarly, if you see that the volume loop is not coming back to normal, so you see it comes down, but again then there is another breath which is being initiated, then there could be different reasons for that. It simply means that there might be an air leak somewhere. So you have to see whether the tube is not proper, like if you don't have a proper cuff tube or there are leak around the tube, then you might see these types of where the flow is not coming down. So there is some form of leak. So this is how you read some of the ventilator scalars. Okay, so let's move on and discuss how do we interpret the different loop forms. So there are two types of loop forms, the flow volume loop and the pressure volume loop. So here is the flow volume loop, and the flow volume loop, you can see, let me take a highlighter color, and here you can see that on the y-axis we've got the flow, on the x-axis we've got the volume. So what happens during in this whole breath cycle, you can see that the volume increase is gradually increasing, and the flow is increasing, and the flow then becomes negative as we go in the expiration phase, and then it comes back to the baseline. And same goes with the volume increases and then it goes down to. So the thing is that you normally see a pattern like this. So if you have got a sort of a seesaw appearance of this phase or the expiratory phase, then we call it as scooping and or seesaw appearance. So it can be because of secretions or obstruction anywhere in the airways. More important is the pressure volume loop. So in the pressure volume loop, what happens, you will see a sort of this balloon like structure. So This is the this is the inspiration, and then that is the expiration. So what happens, as the air comes in, the pressure is increasing. A time comes where all of a sudden you will see a sharp increase in the volume. So what is happening at this is the critical opening point. At this critical opening point, the alveoli, they snap open. So what would happen as they snap open? The volume increases because now the air is going inside, and oxygenation and ventilation takes place. So the oxygen goes inside into the blood, carbon dioxide comes back, and then it comes back. So this is the critical closing point. At this point, the alveoli would close or would come down to their minimum level, and it comes back to zero. So normally you would see a balloon-like. If you see this side of a tail appearance, which we call as a fish tail thing, if you see it on the pressure volume loop, it simply means increased work of breathing. And increase of work of breathing, so you have to check either the sensitivity and see what's triggering that. If you see a beak-like appearance over here, beak-like, so it simply means over distension, because there is more volume of air going inside. The pressures are also increasing, so there is either over distension, which can lead to barotrauma. Similarly, if you see that the this balloon is either shifted vertically up or is shifted horizontally, that can also give you some indication what's going wrong. So if it is shifted upward, it simply means increased compliance. So increased compliance, though generally it's a good thing, but sometimes increased compliance can be because of emphysema and other conditions as well. While if the balloon is shifted downward in this direction, it simply means decreased compliance. Again, I told you decreased compliance could be because of pneumothorax, could be because of increased edema in the lung interstitium, or it could be simply because of ARDS. So this is how you interpret the loop forms on the mechanical ventilator. Now these things are quite extensive. There are a few other modes as well, but obviously, I mean, that is not the scope of this lecture, because you have to read a textbook of pediatric mechanical ventilation to understand this. But I just wanted to make it simple, so at least you can understand some basic things, very basic things. And again, if you go through these things, this probably incorporates 90 to 95% of the problems and the issues that we see in case of pediatric mechanical ventilation. Only 5-10% would be more complex, complicated issues, which in either case are beyond the scope of this lecture. But anyhow, this would make you an expert in dealing with probably 90-95% of the common problems associated with mechanical ventilation. So I hope I have tried to explain it in as simple language as possible. If you still don't understand anything, you can put down a comment below, and I will try to explain it in the comment section below. If you like this lecture, a subscribe would be fantastic. Do share it with your friends, like it, and have a good day. Bye.